All right. Let me just stop and then do it again. And hopefully I will not have any problems. All right. How about now? Yeah, okay. All right, all good. All right. Thank you so much, everyone. Okay. All right. Okay. Okay. I'm just testing everything right now. Okay. Oh, okay, so this class will be about uh, multiple oops, integrals. Okay, and okay. So we'll start by looking at the a review on what you know about integrals. It might take me some time to get used to online teaching. All right. Okay. This is a bit too big. Okay. Uh, so we'll talk first about. We're gonna review first um, the definition of the integral. Okay. Okay. So in the one-dimensional case. Uh, okay. So suppose you have. I really hope that I'm gonna be clear and clean. First time I'm gonna use iPad to teach. All right. So we'll start by the definition of first one variable function. So suppose you have a function f(x) defined on an interval x between a and b. Okay, and we would like to integrate this function. So what was the idea? So the idea was to we divide this we divide the interval AB into subintervals. Remember, right? We call them A, I, B, I. Okay? And each one has a width delta x equal to b minus b minus a over n for some n natural number, okay? Then what we do? Then we choose a sample point or a random point or whatever you want to call it. Sample point xi, we're going to call it xi that belongs to this interval ai bi, okay? So concretely, what does this means? Means that, oops, let me try some technology here to make things. Yeah, so concretely what this means is if I have a function and I have the interval a and b, right? So what I do is I divide this one into small intervals and then call it a1. This one will be a1 and this one will be a2. This one will be a1, a3, and so on. Oh, no, sorry. Just to not confuse you, we'll just call them A1, B1, A2, B2, right? A1, B1, A2, B2, and so on, right? Until AN, B. AN minus 1, BN minus BN, which will be B. So that's the function fx. And then what we do is we then consider the sum, the Riemann sum from 1 to n of this point. Yeah. So here, each point here, we're gonna choose a point which belongs to, let me just type it. We choose a point that belongs to these intervals. We call it xn. X, for example, this one will be called x2 star, right? And this one has the image here, right? And then what we do, we consider this sum here, xi star times delta x, right? So concretely speaking, it means that I will look at the function here f of x2 star, right? And then we'll take this times the interval here, a2, b2. So in this case, it will be something like this. Right, so it will be something like this. Okay, so this will be b2 minus a2 over n, which is delta x, which is this, the width of the basis of this rectangle. And then we multiply by the value of x2, of x2 star. And this is exactly this quantity here, right? That's the area of this rectangle here. Okay? Oops. The area of this rectangle here. Okay? And then we do the same thing for everyone, for every interval, right? So now you can remember that as you're gonna increase n, these rectangles, they will be smaller and smaller. And we'll have a better approximation because remember, this is just an approximation. You can over evaluate this area under the graph because you can miss something or go over the outside the region by this rectangle. So the idea is to what's the idea? So the idea is to they consider the Riemann sum, and we take the limit uh, we take the limit. Sorry, she's not my best friend. And then we take the limit and goes to infinity. So when this series, converges, or I'm gonna call it a sum, because when the sum converges, because it doesn't necessarily give something when you go to infinity. We call it the definite integral of the function fx from a to b, right? And then we use the notation, the integral from a to b of fx dx is the limit when n goes to infinity of the sum from I to n of f star delta x. Okay? And eventually, when you go to the limit, you would get all of the area here. You get all the area under the graph, right? Because you're gonna have smaller, as I say, smaller rectangles. So that's gonna approximate all of this area here. Okay, and this is the integral when f is positive. We're gonna stick with f positive for many of our cases, just to fix the ideas. So what is now the what we want to do is the following thing: is we want to extend this idea to two-dimensional functions. You've been learning about functions, right? And you've been learning about two variable functions for a while. So we would like to do the same thing for two variable functions. So now we're gonna do the same thing for the volume. The volume and double integral. So the thing is, the idea will be exactly the same, but we're gonna go over it again just to make sure that you understand where this comes from. But the only thing is about the two-dimensional case is a bit more complicated. Why? Because remember, in the one-dimensional case, we only have one interval, right? And the integrator over one interval. In two-dimensional case, you will have much more shades than intervals. So we'll start with intervals in 2 dimensions. What are intervals in 2 dimensions? These are rectangles. So we start by, well, so we consider a function we consider a function f x y defined over a rectangle r a b times c, right? Okay. So what is this is the right, so the rectangle in 2 dimensional cases is all the is the all the points in R2 such that X is between A and B and Y is between C and B. Now these are rectangles. These are the right way to. And for now, just to fix the ideas, and for now, just as we did for the 1-dimensional case, and for now, suppose that fx y is larger than 0. Just to give you an idea and visualize everything. For all x and r in R, sorry, in R, in R, okay? Uh, okay. Okay, so let me do a graph again, hopefully. Okay, okay. So we have the two. So here, in this class, you will have to, if you don't, you will have to get comfortable with 3-dimensional uh, technical graphing. Okay, so this is the x-axis. So this is the x-axis, this is the y, and this is z. Okay, and we have a rectangle from A to B, and we have a rectangle from C to D, and uh, that's the rectangle. So this is our rectangle, and this is the rectangle R. And above this rectangle, there will be some function. Okay, there will be some function. Trying to change the color so that maybe it's gonna be a bit easier. There will be some function here. Okay, now there's a function. No, not the right way. Sorry. So okay, some function. Okay, here. That's the function here. Okay, this is fx. This is fx. This is z equal to fxy. So that's the function. And yeah, now we would like to evaluate the volume here, the volume under the graph here. This is the, we would like to evaluate this volume here under this function here. That's the analog of the area when we have a one-dimensional function, right? So that's the goal of double integrals. It's not a cube; it's a function in general. Something weird here might be something like I don't know. It's not easier. It's not easy in general. Might be something like something like this, right? So. So what's the idea? The idea is the same thing. We're going to divide this rectangle and consider columns instead of rectangles. So just to make things a bit more definite, so consider the solid as the lies above the rectangle R, right? And under f x y. So the solid here is given by all the points x, y, z in R3. This is R3, right? We are in R3, such that z is between 0 and the function fxy, and xy is in the rectangle. I keep 2 and R. Okay, so that's the solid here. And this is the solid S. Okay? Uh, so what we do is we will divide just like in the one-dimensional case. We will divide uh, uh, the rectangle uh, R into subrectangles, right? So how do we do that? We divide AB. Whoops. Hello, everyone. Yeah. Am I right now? Is everything okay? Yeah. Oh, Okay, let me just see. Yeah. Okay, let me just see what I can do. Is there anyone joining the meeting? Okay. Stop the video. Okay. Okay. So please try to join the meeting on time because while I will be delivering the class, I cannot keep track on people who come late. So thank you for reminding me. Uh, yeah. So you guys can see right now, everything is okay. I can see that some people, they have a laggy and very slow connection. Is this all right for everyone? Uh, so let's try right now without the video and see how it's gonna go. Hopefully, yeah. Okay. Yeah. Still admitting people. Okay, we can continue, I guess. Okay, let me keep the chat somewhere so I can see. Okay. Okay, so what we do is we're gonna divide the rectangle R into sub-rectangles, and the way we do that is we're gonna divide AB as we did in the first case, in the one-dimensional case, into into n sub-rectangles, sub-intervals. xi uh, xi minus 1 xi with equal with delta x equal to b minus a over n. So n, we're gonna fix some n. We're gonna fix some m, some natural number, okay? And, uh, and we do the same thing for CD, okay? And CD into n subintervals, okay? And we're gonna call them y I minus yj minus 1. So yj minus 1, yj, right? So please, if I'm going slow or I'm going very quickly or on something, but let me know. You can use reactions, I guess. There are some reactions. Hopefully I'm gonna see them. Or if you don't get something or something is not clear, use the reactions. I guess there are somewhere, like thumbs up or thumbs down or something like that. Or the chat, but as long as the chat is not packed and not a lot of people trying to talk, I would keep looking at the chat from time to time. Into n subintervals, the same thing of equal with delta y equal to b minus c, and we divide by the number of rectangles we have. Okay, so concretely speaking, this will look like this. So we have the rectangle, right? We have the rectangle. okay? And what we do is we're gonna divide this. So we have A, B, we have, this is a projection on the x-axis. So we have A, we have B, no, sorry, this is not confuse you. This is the rectangle, and it is somewhere in the XY plane, right? It's somewhere in the X plane. This is X, this is X, and this is Y, and we have A, B, right? And we have C, and we have D, and B, this is the Y-axis, right? Right? And then what we do is we gonna divide this rectangle into small rectangles by doing this, right? And the same thing here. Let me just keep doing just few of them, right? Uh, so this one will be called A, for example, if you take this one, right? This will be called A1. Okay. We're gonna call this one A0, X0, X1, X1, X2, X2, X4, right? And then here we have Y0, Y1, Y2, Y3. So this one will be Y0, Y01, 1, 2, 0, 1, 1, 2. Next you see Y2, Y3. So yeah. So for example, this one here will be, yeah. Okay. And then, so this will be our rectangle, and this will be our subrectangles. So these are like, we are subrectangles. This is a subrectangle. Okay. So these subrectangles, they look like this, right? So this one will be called, uh, for example, in this case, we call it R4, 3, right? We go with it, 4, 3, and we go with the upper point here in the corner, 3, 4, 3. It's just a convention to label this rectangle. But this is very technical, very theoretical, just to understand the idea. You don't need to be very specific. Just fix the notations. It has nothing to do with it. Okay, so these rectangles, they look like this, right? So x, I, minus 1, y, 1. xi times y, j minus 1, yj, right? And then again, then we choose a point x, I, y, j inside this rectangle here. Like for example, I mean, you can choose whatever you want. Like, it doesn't matter. As long as it is inside the the rectangle, it doesn't matter. Oops. For example, this point here will be called x uh, 4 y 3. This very specific example. Of course, you can have much more, right? Okay. All right. So okay. So if you choose this point, we can then approximate the part of S that lies above the rectangle R I J by a thin column with base, this small rectangle Rij, and it has a height of f x y xi star fy star. So that's exactly the same thing as we did in the two cases. So concretely speaking, what we did here is so I'm going back to the three-dimensional case. We divided this rectangle here into a very small rectangle here. That was our small rectangle, RAG, right? That was a small rectangle. And what we did is uh, we have the area of this rectangle. And what we will do is we're gonna look at this point. Remember, the point was chosen inside this rectangle. So it has some image here, right? On the graph of the function. It's called f of x star y j star, right? And what we'll have so what, and then what we do then uh, so what is the volume of the column that is here, this column here, that is just with bases this very small rectangle and height equal to fxi star fyj star. This is just the normal formula. It's the area of the base times the height of the column. So if you want to approximate this thing, we can then approximate the car with, yeah. So the volume of this, so the volume of this box, you're gonna call it a box or a column or whatever you want, is given by the area, right? It's the area of the rectangle times the height of the height of the function xij yi j star. Okay, so that's exactly here. That's the box I'm talking about. Look at the box I'm talking about here. There's a box here, a box here. Right? Trying to, I don't know if I can do that here, but the idea is clear, right? So we will have a box here, right? And so we'll have a box here, right? Like the point here is fxi star y star, and then this will be the box. Hope it's clear. So this is one box, and what we do is we do it for everyone, for every box here. Uh, this was our rectangle, so we do it for all the others, right? Here, all these we can do the same idea, uh, right? And so what happens when you do it for all of these? So so if we so if we add the volumes of these boxes, we get an approximation of the total volume that we are looking for. Total volume that you're looking for under x of x. Okay? So what is this volume? This volume is if you take some very, very large n, if you try to subdivide this rectangles into some very, very large number n and some very, very large number m, you will have very, very, very tiny rectangles. And the more you're gonna do this, the more you're gonna have a better approximation of the volume you're looking for. Because here it might be fxy, uh, fxy star, fj, fyj star might be, the surface might not be the same everywhere. So you might go above the surface when you take the, so you might over evaluate this volume, or it might be some local minima, and then maybe you can underestimate the volume. So the same thing, it's exactly the same idea as in the one-dimensional case. It's just, oh, sorry. I had a FaceTime call. Sorry, guys. I don't know. How can I still FaceTime? Okay. Hopefully, nothing urgent. Uh, who's calling me? Sorry. Sorry. Yeah. Okay. Just make sure that you're not gonna be calling me back. Okay. Uh, so as I was saying, it's exactly the same idea as the one-dimensional case, but it's just you have to make it a case. we do it again. So as you're gonna increase the number of n and m, you're gonna have much better approximations. So you can say that the volume is approximately these very large numbers, but then you have to make the summation over all the boxes you have, from I to n and from j to m, and then you have to add this area, volume, sorry, when n and m are very large. Okay, all right. Let me stop here for for 10 minutes, and then we'll continue. So please, if you think that I'm going so fast or I'm not doing something right, or I'm not explaining very well, please let me know. Don't be shy. No one is perfect, and I can accept every kind of comments you have. So please let me know. Uh, okay, so 10 minutes break, and hopefully I'm gonna see you again. Yes, of course. So this is just an introduction to the double volume. So we're gonna do a couple of examples. We're gonna do a couple of examples. Uh, so for this week, we're gonna cover section uh, 15.1 and section 15.4, four of them. Yeah. So today my plan is to introduce you to double integrals and then teach you how to do them and over regions that are not rectangles, and then do Fubini's theorem, and then tomorrow we'll do applications and polar coordinates. Okay, that might not be a good idea. let us evaluate uh, the integral, the integrated integral from 0 to 3, 0 to 2, x, y, x squared, y, dy, dx. So what you do is you take this function here and you compute this thing. So that's the two process. So the two times process is so we first compute the integral from 0 to 2 of this thing here. But remember, we are fixing x. So this is a one-dimensional integral, right? For some fixed x. Okay, for some fixed x. So what is this? So this will be ax. So ax will be equal to the integral from 0. I'm just repeating myself here. dy. Now this is a constant right now, right? This is a constant. It's a fixed x. So we can put it out, x squared, the integral from 0 to 2, y dy, which will be equal to x squared times 1 over 2 y squared between, here is very important to not like the one-dimensional case where you just write down numbers here on the boundaries, but here it's very important to write y between 2 and y equal to 0. Yeah. If we are fixing x, y is the integral, ax shouldn't be ay. No, because y is it? No, because here, if you write down ay, it means that y is fixed, right? But y is not fixed. Y is changing here. It doesn't make sense to write this. This does not depend on y because you're integrating over y. So for some x, you integrate from 0 to 2, where y varies from 0 to 2. So it doesn't make sense to write what is y. If you suppose you write down this is equal to ay, right, for some fixed x. All right, so forget about this. This is the right answer, so forget about this one for now. So what doesn't make sense because what is y? Y is already absorbed in the integral. Like the integral, the job of the integral is to forget about the variable. It just takes the global thing, right? It's like between 0 and 2, and we just try to sum all of the y. So it doesn't make sense. This one will give you something that depends on x, as you're gonna see here, and this will depend on y. So we're gonna see this. You will see this in the example. For example, what is this? This is equal to x squared times, just as you do in the one-dimensional case, will be 2 squared, which is 4 over 2, minus 0, which will be 2x squared, right? So, all right. No, sorry. This is 1, because I don't want to make any errors. So just let me stick to my notes. So this is 0, 2, and this is 1. So here we have 1. So here we have 1. Okay, so here we have 1 over 2, which is equal to which is equal to 3.5 x squared, right? All right, so you see here, if you see ay, it doesn't make sense, right? Here you have 3 over 2x squared, and you have ay. It doesn't make sense. So here it depends on x. So this is the function of x. Ax is equal to 3 over 2, and then I can integrate this thing here from 0 to ax dx, which will be the integral from 0 to 2, 3 over 2x squared dx. And then as you're familiar with these calculations, this is not a course, and you already know how to do these things. So it's x cubed over 3. Now you can drop down which one is what. Now you can just leave 3 and 0, but don't do it here, because don't do it here. Because the TA will not know what you're doing, right? Don't do it here. Which will be 27 over 2. Okay, so that's exactly this one. So of course you can do it the other way around, starting by x and y, and it's gonna give you the right answer. So the one of the early big achievements of this area of mathematics is I think the answer. Oh, sorry. Yeah, it's a good thing to keep looking at the chat, because I can make errors. And oh, it's 27 over 2. Yeah, it's 27 over 2. Trying to be very, okay. So these are calculations. Just make sure that that you don't make any errors. It should be very straightforward. Just don't make any errors. When I was a TA, I really didn't. I mean, when I was a TA, I really didn't care about. It's not like I didn't care, but as long as you have this and this, and you put like 1 here, I wouldn't care. I know, like it's a bit, if you are an engineer, or it might be crucial, because people's life will be on your hand if you're trying to build some bridge or something, but we're not engineers, right? So of course. Okay, so just make sure that you got the right things, like this and this, right? And then you can compute things very carefully when you're alone. Okay. All right. So one of the big achievements of this area is that these two ways of computing, right? These iterated integrals, by starting by dy and dx and then doing it the other way around, in a lot of cases, and actually in all the cases we'll be encountering in our class, they will be the same. That's a big thing. In the examples and the exercises, you will see why it's a good thing. So the following, it's called Fubini theorem. The following theorem is of crucial importance. It provides. Now, it's not only that. So this theorem is more than what I just said. I will be clear right now. It provides. So right now, remember, I didn't really talk about the integral. What I did actually is I moved from the volume limits, and then I just went to some very calculus, some one variable calculus. But the following theorem will give you a way to evaluate this very hard limit, right? Right? Because if you really want to compute the volume, you need to go to the limit. But the following theorem will make your life easier, and it will tell you the following thing. It will tell you that, so we have a theorem, So of course we have some very technical all right, some very technical hypotheses. If f is continuous on the rectangle, and what I mean, this here, I know some of you will not care because but in the exercises you will see that when this hypothesis is not true, on the theorem is not true. If f is continuous on the rectangle, and of course you really know right now, I'm not gonna go over it again. I'm not gonna recall what it means, but you should know right now what the function of two variables, what does it mean to be continuous, right? So if you don't, just go back. It's a bit harder than continuity in one case, in one-dimensional case. On the rectangle R, so if it's continuous on the rectangle R, which is equal to AB times CB, then be careful here. It says three things here, and it's really important to know what it means. It says that the integral that we've been looking for, and we did the limits and all of that, right? This integral that allows you to compute the volume. You don't need to do the limit, divide, and then go to the limit, because in any case, in most of the cases, you won't be able to compute the limit. It's very hard. You don't need to do this subdivision thing. You just have to compute what we just did. This very calculus thing, you just have to compute this thing. AB and then CD of the function fx, y, dy, dx, right? This is iterated integral. So that's what it says. Moreover, it says that, again, if the function is continuous and all of that, it is also equal to the other one we considered, which is the integral from a to b, from c to d, of x, y, dx, dy. So there are three things here. These two are equal, and they both give you the volume under the function, right? So this is a very technical theorem. We're not going to prove it. It's very hard to prove in a very specific way and all of the examples, but there is, I mean, I don't know, it's 12 o'clock, and hopefully, what's the plan for today? The plan is to do this, and then regions, and then properties of double integral. Okay, let me give you a very heuristic way to understand why is this true. So we have a remark here. There are some other cases, like less demanding than the continuity, but it's not really very relevant in our case. But the theorem says it's also true when, for example, when f is bounded. This theorem, this is called Fubini's theorem. Let me just call it, just make sure that you understand. This is called Fubini's theorem. Fubini's theorem. Well, so if you look at the history of this theorem, it's quite a recent theorem, around 19 something. And I was quite surprised in the beginning when I learned that, because this area of math, it's been around from from really a long time, around 1700 and 1600, because as soon as possible, people they discovered calculus, they went to two variable. But then the reason why it's this is around 19 something, right? It's very recent if you read history of math. And the reason is because this theorem applies for a much harder integral, which is, we're not going to cover this, but it applies for a much abstract form of integrals. And that's why it's only been proved in the early 20th century. All right, so this theorem also is true if it's also true, but I'm just gonna write it. It's also true if f is bounded, right? If it's bounded and this the two the iterated integrals exist, right? And f is this continuous only on a finite number of smooth curves. We're not going to go over this, just for your information. So why is it true? So I'm just going to go over it very quickly. So we are on the three-dimensional case. Okay, and we have a function. We have the rectangle. Okay, we have the rectangle. We have the rectangle here. Okay, we have a rectangle, and above this rectangle, we have the function okay, the function here, and that's our function. Here. Too big. Okay, we have a function here. So this is our surface. And so what we do is we fix, so this is AB, and this is C, and then B, right? So what we do is when we fix some X here, what we do is we actually cut off the surface by the plane X, this plane here, this plane here. Okay, so this is kind of plane, right? So this will be kind of a section, right? The section that will be called, that if you look at the definition of the integral, it will be like the area under the graph. This is the graph. This is the graph of the function when you fix X. It will be kind of function here, one variable function. So when you compute AX, it will give you the area of this thing here, right? Now, when you do the AX, dx, you go over this direction, right? So what you do is you multiply this very area by some very small uh, width here, right? So what you do is you just multiply this area by some very small base, some very small height here, which is dx, right? We could call the small dx. So we do this for everyone, for every kind of, you fix x, you do it, you fix x, you do it, you fix x, you do it. So what you do is you can add up all of these volumes. So that's another way to compute the volume of all of this solid here. Sorry, my voice is lagging. Am I right now? You okay? Yes, good now. All right. So when you evaluate this integral from a to b, you just adapt all of these other ways of computing the volume, right? There are many ways you can compute the volume, like rectangles, columns, boxes. That's another way. So that's a heuristic way to see it. And the same goes around for the other way, right? So if you change the thing, you change if you fix y, for example, then you're gonna have a kind of function here, and then you have a kind of uh, plane here, right? Right? Same thing, right? And then when you fix y, it gives you this kind of plane here. And I don't know if it's really clear, but the way goes, so then you go on this direction dy, right? And then you compute a from C to D, and then this will be again the area of this thing will be given by AY, right? And you fix y, this is some y. Uh, and then you can start adding all of these areas times the height of this, right? And then, of course, they give you the same thing. If everything is okay and nothing wrong happens, in other words, if the function is continuous, and all of that. So that's the way. That's the way. That's why it's true. Okay, so let's do an example. Example. Okay. Uh, okay, now we're gonna evaluate this. Evaluate the integral r x minus 3 y squared dA, where r is the rectangle given by x, y, such that x is between 0 and 2, and y is between 1 and 2. Okay? So now we're gonna compute the very actual thing using Frobenius theorem, right? So using Frobenius theorem, right? You can start by whatever you want, by dy and dx. So let's just do it from one side. It says that this integral, right, the volume, right? But be aware, it's not always the volume, right? It's sometimes when the function is negative, kind of this sense of volume is lost, right? But we're just gonna use the volume because sometimes, just in the one-dimensional case, when the function is not positive everywhere, it can be zero, right? So this integral here, x minus 3 y squared, is given by the formula integral from, so we do it the way dy dx, right? So dy dx, so y here is from 1 to 2, and then x is between 0 and 2. So that's it. Then we're just gonna do calculus, one-dimensional calculus. Right now, we have from 0 to 2. People are still coming. What is x less than? Yeah, x is 2. Yeah. And 1 and 2. Okay, I'm gonna be working on my calligraphy a little bit so that, okay, all right. So now now x is fixed. So this is a function of one variable, y. So it's x, it's a constant. Now, what is the primitive function of the function is xy minus y cubed, right? And then you have to compute this between, as I said before, you have to make sure what is what. So between y equal to 2 and y equal to 1. And then the whole thing, whatever you get, you integrate over x. Now, the integral from 0 to 2, what is this? So now we compute. This is, just compute this thing. It's 2x minus 2 cubed minus x minus 1, right? Dx, which is equal to the integral from 0 to 2, which is x minus 7 dx, okay? And then now we integrate again, which is x squared over 2 minus 7x, the whole thing between 2 and 0, which will be equal to 4 over 2 minus 15 minus 0, which is minus 12. Okay, so that's the volume. It's a negative volume, but we did the volume just to give you an idea of what is an integral. But then the same thing we can do for negative functions. We subdivide. It's gonna give a negative when you're gonna multiply all of these columns and boxes. It's gonna give you negative things. But you just add up all of these negative things, whatever it gives you. By the end, you're gonna have a number. If the function is positive, it's gonna give you the volume. If it's not positive, it's gonna give you a number. All right. Okay, so that's an example. Now you can make sure you can do this on your own, but if, okay, we're gonna do it again, just to illustrate a little bit of Fubini's theorem. So let's do it on the other way. Let's do. We can also uh, use the other iterated integral. And just like, let us make sure that they give the same thing. So for example, Fubini's theorem says that this integral here, x minus 3y dy, is also the integral of this function x minus 3y squared. But now we're gonna start by dx dy, right? Remember, here we started by dy and then dx, okay? Now we'll do it the other way around. Sorry. Yeah, now we're gonna do it by dx and then dy. All right. So now dx is between 0 and 2, and dy is between 1 and 2. Should we take a break? Let me finish this example and then we'll take another break. Because I guess it's each hour. So it's the integral from 1 to 2, dx. Now y is fixed, so it's 3y squared x minus x squared over 2 between x equal to 2 and x equal to 0 dy. Okay? Uh, sorry, plus minus. Okay? This will give you the integral from 1 to 2. If you plug in everything, it's going to give you 2 minus 6y squared dy, right? And then you integrate again. This is 2y minus 2y to the power 3 between 2 and 1, which will be 4 minus 2 times 8 minus 2 minus 2, which is, this is 16 and this is 4, so it's minus 12. So it's the same thing, right? Okay, it's the same thing. Any questions? Okay, so for today, we are, I think we need to do, maybe you can have more examples, but we can maybe do the more general regions, and then double integral and polar coordinates, and then applications. Yeah. So for today, we would like to do double integrals over yeah. So it's moving very fast, but that's a summer class. It's okay. So we'll take a break. Um, yes, so there are some situations where dx dy is not equal to dy dx. So this will be, you do the exercises from problem is, there is an exercise where they're not equal. And you can guess why, because something goes wrong. Continuity is not okay. So yeah. All right, so let me take a break. And then after the break, we're gonna do integrals over more regions, because rectangles are cool, but there are cooler regions. We're gonna integrate over these regions. And yeah, that will be for today. Hopefully I can do this in half an hour. All right, so we'll be back in 12:30. Okay. Let me take, we already. Okay, hello everyone. Let me be back because maybe we're gonna be running out of time at some point. Uh, okay, okay. So double over general regions. Uh, okay. Um, so as I told you, we can integrate. One of the challenges of two-dimensional integration is there are many, much more uh, general regions than rectangle. So for example, we have a rectangle here, and then we, we, we have seen how we can integrate a function over this rectangle here between A and B, and then C, and then D, right? So now, what happens uh, if I have, for example, a bounded region, some region D, right? So what do we do? Uh, so that will be the, the next topic. So we first have to get a definition of this, uh, what we mean by integrating something over a region D, because we have a definition of an integration over R. We know what it means. So what does it mean to integrate something over D? So we consider a function fx defined on R2, right? And a bounded region V inside the plane R2. This is R2. Why bounded? Bounded because we wanna kind of bound this region by a rectangle. So because whenever you give me a bounded region, I can find something that is again bounded by a rectangle. So that's exactly the definition of a bounded region. You have a region, whatever the form of this region, I can bound it by some rectangle, right? That's the meaning of of uh, of a of a bounded region. That's going to be a rectangle, right? And this will be our region P. Okay, so that's what we do. We take the region bounded by a rectangle, right? And then define uh, the function, then define uh, the integral, right, over the rectangle R of this other function dA. Now we know the meaning of this because we only talked about integrals over rectangles. But now we have to know what is this f. where f x y will be the function fx y if x and y are inside D, 0 otherwise. Okay? So that's exactly the definition of an integral. If you give me a function and it's defined on the region D, if you want to integrate this function f on the region D, take this function capital F defined by this, and then integrate these capital F functions on the region R. And we know what is the meaning of this. We've been talking about this for 2 hours. So we know that's the meaning of this. So that's the integral of a function over a domain D. But concretely, what does it mean? Concretely, it means that, sorry, yeah. So concretely, it means that you only consider the function here, because otherwise it's 0 outside. Here it's 0, but here it's equal to fxy. So there are several regions that we can consider. Um, uh, okay, so there is what is called type 1 regions. So these are regions that they look like this. Right? These regions have the following form. So it's D equal to x, y, such that x is between some 2 real numbers, but y is allowed to vary between 2 functions, gy, sorry, let me change the color here, between a function gx and hx, g1 and g2 of x. Okay, where, and again, we're gonna just consider functions that are, regions that are smooth, where g1 and g2 are continuous. So concretely, what does it mean? It means that I have my RT plane, okay? This is X, this is Y, and I have A, and I have B, and then I can have, so X is between X, but Y will be allowed to have, sorry, where is B? Yeah, will be allowed to be like this. For example, this is an example of a region. So this is some function, or even more general than this. Even more general than this. You can have a function here, right? But then here you'll have another function. Right? So that's a function g2, and this is a function g1, and x is between a and b, and y is varies from, so if you fix some y here, it will be from G1 to G2, right? So that's an example of a region V. There are several other examples. It's really not, that's not the only way you can have. You can have, for example, sorry, you can have, for example, AB. You can have, for example, same thing, AB, okay? And then you will have something that looks like, this is B, you'll have something like this, right? So for some Y, it's between this function here, gyx, d2x, g1, and g2. So these are examples. So this is region B, this is region B, okay? Uh, so okay, so for this type of regions, what do we have? So what is this integral here? So for this type of regions, we'll have the integral of this function here, right? This is by definition. This is by definition, right? It is equal to the integral of r, right? Because we can always bound by some rectangle here, right? A rectangle that contains these regions. Remember, that's the definition, right? Of some rectangle r of the function f x y d dA, right? Which will be equal to the integral from C to D, the integral from A to B of f x y dy dx. So again, go back. I'm sorry if I'm going back and forth from this. No, it's not the best thing, but just to save some time, 15 more minutes. I'm talking about this rectangle here, AB and CD, and this region here, D, looks like something like this. Looks like this, right? So this is what I mean here by A, B, and C. Since f x y is equal to 0 for y larger than g2 of x and less than g1, and f x y is equal to f x y for g1, right? Right? So we can compute this thing because if it's 0 outside, you can just forget it. So we're gonna have this we obtain that the integral from C, sorry, I just have to make sure that, yeah. I think it's confused here. There's a typo. Please correct this typo. Here it's not dy. It's ab. I think it's, yeah. There's a typo here. So here we want cd. Because remember, it's continuous. It's the same thing. Yeah. AB. And here it's dy dx. In particular, we can do this because we have the freedom of choosing which one we'll do first by Fubini's theorem. But for this type of regions, it's good to start by y and then dx. So what will happen is this integral here, this one, the one that is inside, will be equal to dx, because as I said here, it's 0 outside G2x, and it's 0, sorry, it's 0 if it's not inside this region. So this will be equal to the integral from c to d of fx y. But now, c to d, I know what are these c to d, right? I know what's the boundary. It's between g1 and g2. Okay? So, for for uh, for regions of type 1, we have, so for this kind of regions, should be AB then CD. As I said, you have the freedom. Here, you have the freedom. Uh, B, Y is between C and D, and X is between A and B. But you can do it the other way around, but it's not gonna be really, for this kind of regions, it is harder to do it that way, right? And that's the right order to take in this kind of regions. Uh, so for this kind of regions, the integral of over a region D of type 1 of a function fx y dA will be equal to the integral from a to b, the integral from the function g1 of x to the function g2 of x of the function fxy, right? dy and then dx. And it makes sense because then you're gonna fix x, integrate over y, and then whatever you get, you integrate over x. I know maybe it's the first time you're gonna see this, but you need an example. So we're gonna do a couple of examples, but let me just do for type 2. Type 2 regions are exactly the same thing, but just flip over. Like just let me like write down what it means. I'm gonna go over it quickly, and then we'll do examples so that it's a concrete thing. So type 2 regions. Type 2 regions are exactly the same thing, but they have the following forms. Type 2 regions have the following form. It's D xy such that y is between C and D, but then x is between two functions of y. Let us call them h in this case. h1 of y and h2 of y. Okay? And so an example would be, for example, we are in the R2 case. We have C and D. Okay? We can have this, we can have this, and then right? So that's a region of type 2. That's the example, right? And again, we always uh, assume that these functions h1 and h2 are smooth, they're continuous, so that nothing is wrong with the nothing really pathological with the region D. And then you can do the same thing, but then you just have to be careful. But you have to start by integrating. Just do the same thing. I'm not gonna do it, but do the same thing. Start with the definition. Find the rectangle that it contains the region D, and then start by dx and then dy, and then because dx, now you're gonna have x. Now you're gonna have x. Now you're gonna have x. Sorry. Now you're gonna have x, and then you have uh, y. Now, because x, now, for example, if you choose a rectangle that contains this region, outside this region, it's 0, and inside it's f. So you just have to stay within these two boundaries, which is h1 of y and h2. And then whatever you get, you integrate from c to d, right? So instead of starting by a, you're going to have ab, you're going to have cd, but then here we're going to have h1, h2. So a similar so a similar argument shows, but don't worry, I'm gonna do examples and you're gonna understand much more. This is just to introduce you to the idea, and then best way to do these kind of things and to do every kind of math is just do examples. So a similar argument shows that uh, for this type of regions, for these regions, uh, the integral of the function f xy dA over the region D it will be equal to the integral from C to D, and then the integral from the function h1 of y to the function h2 of y of the function fxy dx dy, right? So that's what we do for this type of regions. Now be aware that in some cases you will have a region that is not a region 1, that is not a type 1 region, nor a region of type 2. That can happen. So that's another, I think there's an exercise. There are many exercises you can try from the book, but there is one. I think I included this one from the problem set, uh, which will ask you to divide. I'll give you a region that is not type 1 or type 2, and then I will ask you to divide it into two regions. And these two regions, there will be one of them will be type 1, the other one is type 2. then you can compute the integral. So let us do an example. We still have 5 minutes. Let me try to see what I can do in 5 minutes. Example. Compute, evaluate the integral b where d is the region bounded by y equal to 2x squared and y equal to 1 plus x squared. Okay? So in concretely speaking, this will look like this. So we'll have the first function, 2x, which will be something like this. Sorry. Which will be like something like this. Okay, so the first one, this is y equal to 2x squared, right? And then you will have another one that starts at 1, but then you'll have a little bit of eccentricity, less than, you like it more flat. That will be the other region. So this one is y equal to 2x squared. Then from x2, and then this one will be y equal to 1 plus x squared. So the first thing we need to do for all of these cases is we need to find, so the region we're talking about is this one. That's the region we're talking about. That's the region. Okay? That's the region, D. Call it D. Okay? So first thing we do is we find the intersection. That's something you need to always to do. Find the intersection. This is the intersection, right? So I know I should have started this on a new page. Sorry for the person who asked me, but anyway, we'll not finish this example right now. But let me just write down here the intersection. So always find the intersection. Is given by. So when do they intersect? You know, it's when 2x squared is equal to 1 plus x squared. This means that x squared is equal to 1, which means that x is equal to plus or minus 1. So this one will be 1, and this one will be minus 1. Right? So now we can see that this is a type of region 1. So it's because x is between minus 1 and 1, it's at A and B, right? And for each x, right, remember, this is just an example. For each x, I have that y is between this function here and this function here. So so this is a type 1 region. Okay. All right, so it's 1 o'clock. I think we'll stop here and we will continue the example tomorrow. Uh, uh, Hopefully was nice, and yeah. Let me know, guys, if you have any questions or you want something to be improved or you have any questions. I'm free to answer any of those. So, okay, thank you so much. And we'll see you tomorrow then.